Beneath the waves far below storms, ships, and even sunlight, something vast is moving. It doesn't surge, it doesn't crash, it doesn't make a sound. Yet, it never stops. Right now, a hidden network of deep ocean currents is flowing through the planet's oceans, carrying heat, oxygen, carbon, and nutrients across the globe. It links the Atlantic, Pacific, Indian, and Southern Oceans into a single connected system, one that quietly shapes Earth's climate and sustains life. This system doesn't just influence the planet, it powers it. Without these deep currents, Earth would look radically different. Large regions would be locked in colder climates. Marine ecosystems would lose the nutrients they depend on. Carbon dioxide would accumulate in the atmosphere far faster, pushing the climate toward extremes. And here's the most astonishing part. This planetary engine moves at a pace almost too slow to notice. A single drop of water can take nearly 1,000 years to complete its journey through the deep ocean. Today, we're diving into the deep ocean water currents that make Earth habitable, and why the stability of our planet depends on motion we can't see. What are deep ocean currents? When most people hear the words ocean currents, they picture what happens at the surface, fast-moving streams of water like the Gulf Stream or the Kuroshio Current, carving paths across the ocean and shaping weather above. Those currents matter, but they're only the visible layer of a much larger system. Far below the surface, thousands of meters down the ocean moves in a very different way. This is the deep ocean, a realm of near-total darkness, crushing pressure, and temperatures that barely change over centuries. Here, the water doesn't move because of the wind. It moves because of density. Seawater density is controlled by two variables, temperature and salinity. Cold water is heavier than warm water. Saltier water is heavier than fresh water. When surface seawater becomes cold enough and salty enough, it gains weight, and once it reaches a critical density, gravity takes over. The water sinks. This sinking is not chaotic or random. It happens in specific regions of the world, and when it does, it pulls surrounding water along with it, setting vast volumes of the deep ocean into motion. That process is the engine behind thermohaline circulation, named for thermo, meaning heat, and haline, meaning salt. Scientists often describe this system as the global ocean conveyor belt, not because it moves quickly, but because it moves continuously, transporting heat, carbon, oxygen, and nutrients across every major ocean basin on Earth. And it operates on a planetary scale. While surface currents shape weather patterns, deep ocean currents shape the long-term stability of Earth itself. And this is only the beginning of the journey, where the ocean falls into itself. Deep ocean circulation doesn't begin everywhere. In fact, it begins in only a handful of places on Earth, locations so extreme that the ocean itself becomes heavy enough to sink. The most important of these regions lie in the North Atlantic and in the waters surrounding Antarctica. In these polar environments, the ocean is exposed to relentless cold. As surface seawater loses heat to the atmosphere, its temperature drops and its density increases. But cooling alone isn't enough to drive the deepest currents on the planet. Something else happens here, something critical. When sea ice forms, it doesn't trap salt inside it. The salt is pushed out, left behind in the surrounding water. This process increases the salinity of the remaining liquid seawater, making it even denser. The result is a powerful combination: water that is both intensely cold and unusually salty. Heavy. Eventually, this water reaches a tipping point. Gravity takes over, and the ocean begins to sink into itself. Dense surface water plunges downward, sometimes falling several kilometers toward the seafloor in massive, slow-motion cascades. This is how some of the most important water masses on Earth. In the North Atlantic, this sinking creates North Atlantic deep water, a key driver of global circulation. Around Antarctica, the process forms Antarctic bottom water, the coldest and densest seawater on the planet, spreading beneath every other water mass in the global ocean. These regions are rare. Only a small fraction of the ocean's surface is capable of producing deep water like this. But their impact is enormous. When water sinks here, It displaces deep water elsewhere, setting the entire global circulation system into motion. And once this water descends into the deep ocean, it doesn't simply settle and rest. It begins a journey that spans entire ocean basins, creeping along the seafloor, threading through underwater ridges and valleys, and slowly connecting the Atlantic, Indian, Pacific, and Southern Oceans into a single, continuous system. This is where the planet's slowest and most powerful movement begins. And from here, the deep ocean carries that motion across the world. The 1,000-year journey. Once deep water sinks, it doesn't rush anywhere. There are no surges, no waves, no visible motion. Instead, the ocean begins one of the slowest journeys on the planet. Newly formed deep water spreads outward from its sinking regions and creeps along the ocean floor, guided by the shape of the seabed itself. Vast underwater mountain ranges, deep trenches, and narrow passages all influence its path, steering these currents across entire ocean basins. From the North Atlantic, deep water flows southward, hugging the bottom of the Atlantic Ocean. It continues toward the Southern Ocean, where currents from different basins converge and circle Antarctica. From there, this deep water is gradually distributed into the Indian and Pacific Oceans, filling the deepest layers of the global ocean. The speed of this movement is almost impossible to imagine. In many places, deep ocean currents travel at just a few centimeters per second. That's slower than the minute hand of a clock moving across a page. A person walking at a normal pace could outpace these currents without noticing any resistance at all. And yet, despite their slowness, they move more water than any river system on Earth. These currents span thousands of kilometers and involve enormous volumes of water. Layer by layer, they transport cold, dense water across the planet, shaping ocean chemistry and temperature far below the surface. This journey is not short. From the moment a parcel of water sinks in the North Atlantic or near Antarctica to the time it eventually returns to the surface, nearly 1,000 years can pass. That means some of the deep water rising today last touched the atmosphere during the early Middle Ages. As deep water flows through the ocean basins, it slowly changes. It picks up dissolved carbon, nutrients released from sinking organic material, and chemical signatures that scientists can trace to understand where the water has been. Eventually, the deep ocean gives that water back. In the Pacific and Indian Oceans, deep water is gradually pulled upward through a process known as upwelling. This rise isn't driven by a single force, but by the combined effects of wind, tides, and mixing caused by underwater topography. Over time, deep water ascends layer by layer toward the surface. As it rises, the water warms, its density decreases, and once it reaches the surface, it rejoins faster-moving surface currents, carrying with it nutrients that fuel marine ecosystems and chemical fingerprints of its long journey through the deep. The cycle closes. Surface currents transport this water once again toward high latitudes, where cooling and increasing salinity can send it sinking back into the depths, restarting the global conveyor belt. This system doesn't operate on human timescales. It works on geological patience. Quiet, steady, and relentless, the deep ocean connects past climates to the present and ensures that Earth's oceans function as a single, integrated system. 1,000 years to circle the planet, and it never stops moving. One of the most powerful roles of deep ocean circulation is something we rarely notice: the steady redistribution of heat across the planet. The ocean doesn't just store heat, it moves it constantly on a global scale. At the surface, warm currents carry heat away from the tropics toward higher latitudes. These waters release energy into the atmosphere, but for this system to work, warm water has to be replaced. That's where the deep ocean comes in. As surface water cools and sinks in polar regions, it pulls warmer surface water northward to take its place. In doing so, the ocean creates a continuous exchange: warm water flowing poleward at the surface, cold water returning equatorward at depth. This vertical and horizontal movement forms a planetary heat engine that operates year. A striking example of this process can be seen in Western Europe. Cities like London and Paris sit at the same latitude as parts of eastern Canada, yet their winters are far milder. This difference exists largely because of ocean heat transport. Warm water carried northward across the Atlantic releases heat into the atmosphere before cooling and sinking. Without that deep water sinking in the North Atlantic, the flow of warm surface water would weaken, and Europe's climate would shift dramatically toward colder extremes. But the influence of deep ocean circulation goes far beyond regional temperature differences. The deep ocean acts as a massive heat reservoir. It absorbs and stores enormous amounts of thermal energy, including heat added to the climate system through natural variability and long-term warming. Because deep water is isolated from the atmosphere, heat stored there can remain out of circulation for centuries, slowing the rate at which the atmosphere warms. This buffering effect is critical. It helps prevent rapid temperature swings and reduces the intensity of short-term climate extremes. In effect, the deep ocean moderates the planet's response to changes in energy balance, acting as a stabilizing force within the climate system. When deep ocean circulation functions normally, heat is distributed gradually and predictably. When it weakens or changes, that balance shifts. Climate patterns can reorganize, temperature contrasts can intensify, and regional climates can change in ways that unfold over decades rather than days. Without the slow, continuous movement of deep currents, Earth would not simply be colder or warmer, it would be far less stable. Seasonal patterns would become more extreme, heat would accumulate unevenly, and the climate system would lose one of its most important regulators. The deep ocean doesn't just respond to climate, it helps control it. The ocean as a carbon vault. The deep ocean is not just a circulation system, it is one of the largest carbon vaults on Earth. Every day, carbon dioxide moves between the atmosphere and the ocean surface. Cold seawater is especially efficient at absorbing carbon dioxide, allowing the ocean to act as a powerful sink for atmospheric carbon. But absorption alone isn't what makes the deep ocean so important. What matters is what happens next. When carbon-rich surface water cools and sinks, it carries dissolved carbon dioxide with it into the depths. Once that carbon enters the deep ocean, it is effectively removed from the atmosphere for extremely long periods of time, often hundreds, and in some cases thousands of years. This process dramatically reduces the amount of carbon dioxide circulating in the air at any given moment. Without it, atmospheric carbon dioxide concentrations would be far higher, and Earth's climate would be far less stable. Deep ocean circulation also plays a critical role in transporting oxygen. When surface waters sink, they carry oxygen with them, delivering it to the deep sea. This prevents vast areas of the ocean from becoming stagnant or depleted of oxygen, conditions that would make much of the deep ocean uninhabitable. At the same time, the deep ocean is constantly accumulating nutrients. As organic material sinks from the surface and decomposes, it releases nutrients into deep water. These nutrients remain stored at depth until circulation slowly brings them back toward the surface. This return happens through upwelling, particularly in parts of the Pacific and Indian Oceans. When deep, nutrient-rich water rises, it fertilizes surface waters, fueling the growth of phytoplankton microscopic organisms that form the base of nearly every marine food web. Some of the most productive fisheries on the planet owe their existence to this process. The nutrients delivered by deep ocean circulation support massive blooms of life, which ripple upward through the ecosystem, sustaining fish populations and, ultimately, human communities. The deep ocean doesn't just store carbon. It regulates oxygen, recycles nutrients, and quietly supports life across the entire planet, all while remaining almost completely out of sight. What happens if the system weakens? Thermohaline circulation is remarkably resilient. It has persisted through ice ages, warming periods, and massive shifts in Earth's climate. But resilient does not mean unchangeable. One of the most important factors controlling this system is salinity, and salinity is directly affected by freshwater input. When large amounts of fresh water enter the ocean, whether from melting ice sheets, retreating glaciers, or increased precipitation, the salt content of surface water decreases. That change may seem small, but in the deep ocean, small differences matter. Less salt means lower density. Lower density means water sinks more slowly or, in some cases, not at all. In regions like the North Atlantic, where deep water formation depends on cold, salty surface water sinking, an influx of fresh water can weaken this process. When sinking slows, the entire circulation system begins to respond. Deep currents weaken. Heat transport shifts. Climate patterns begin to reorganize. These changes don't happen overnight. Thermohaline circulation moves slowly, and so do its disruptions. But when change does occur, its effects can be widespread. Altered ocean circulation can reshape temperature patterns, shift precipitation zones, and change how heat is distributed between the ocean and the atmosphere. We know this because Earth has recorded its own history. Ice cores and ocean sediment records show clear evidence that past disruptions in ocean circulation were linked to abrupt climate changes. In several cases, relatively small shifts in freshwater input were followed by rapid temperature changes across large regions of the planet. What makes this system particularly important is the scale at which it operates. Because deep ocean circulation connects all major ocean basins, changes in one region can propagate globally over time. That's why scientists monitor thermohaline circulation so closely. Instruments placed throughout the ocean track temperature, salinity, and current strength, looking for long-term trends rather than short-term fluctuations. The concern is not collapse in a dramatic sense, but gradual weakening, a slow rebalancing that unfolds over decades. The kind of change that doesn't make headlines at first, but steadily reshapes the climate system beneath the surface. The deep ocean responds patiently, but once it responds, the consequences are felt everywhere. Understanding how this system behaves and how sensitive it is to change is essential to understanding Earth's climate future. Why does this system make Earth habitable? The deep ocean currents don't roar like rivers or crash like storm-driven waves. They move silently, steadily, and almost imperceptibly, yet their influence is enormously far greater than their quiet presence would suggest. These currents are one of the planet's most powerful systems, shaping the environment in ways that touch every corner of the Earth. They regulate climate on a global scale. By moving heat from the equator to the poles and returning cooled water toward lower latitudes, deep currents stabilize temperatures across continents. Without this transport of energy, regions like Western Europe would be far colder, tropical climates could shift dramatically, and seasonal patterns would become far less predictable. They store carbon. By sinking surface water rich in dissolved carbon dioxide into the deep ocean, the currents sequester massive amounts of carbon dioxide, keeping it out of the atmosphere for centuries or even millennia. This process slows the buildup of greenhouse gases, acting as a natural buffer against climate extremes and helping maintain a livable climate. They sustain ecosystems. Nutrients carried by deep water rise to the surface through upwelling, feeding plankton, the foundation of nearly every marine food web. This nutrient recycling supports some of the world's most productive fisheries and maintains biodiversity from microscopic organisms to top predators in the ocean. And they connect the planet. The deep ocean conveyor belt links every major ocean basin, forming a single, integrated system that balances temperature, salinity, oxygen, and nutrient levels across thousands of kilometers. This silent circulation ensures that the oceans function as a coherent, living system rather than isolated bodies of water. Without these currents, Earth would be a harsher, less stable, and far less hospitable place. The climate would swing more dramatically, ecosystems would struggle, and the delicate balance that allows humans and countless other species to thrive could be disrupted. The deep ocean currents are Earth's quiet but unstoppable engine, moving heat, carbon, oxygen, and nutrients across the globe. They regulate climate, store carbon for centuries, sustain marine life, and connect oceans into a single living system. Without them, the world would be colder, less stable, and far less hospitable for life as we know it. These currents remind us that some of the planet's most vital processes are hidden from view, working patiently over centuries to keep our environment balanced. Next time you look at the ocean, think of the vast, slow-moving conveyor belt beneath the silent powerhouse shaping our world. So the next time you look at the ocean, remember, the most important motion isn't what you see on the surface. It's the slow, silent currents moving kilometers below, shaping climate, storing carbon, and feeding life. 1 centimeter at a time, they power the planet quietly, invisibly, and indispensably. If you enjoyed this journey into the deep, don't forget to like, share, and subscribe to our channel.